Good morning, everyone. In the previous video, we have proved that if P is a covering map from E to B, which maps the point E naught to B naught, then the lifting correspondence phi from pi 1 B naught to P inverse B naught. This is surjective mapping if the space E is path connected. And if it is simply connected, then this mapping phi is a bijective map. So now we will prove a stronger version of this result. And this result says that if P is a covering map from E to B, which maps point E naught to B naught, then first of all, the homomorphism which is induced by the mapping P, that is the homomorphism P star from the fundamental group of E with respect to E naught to fundamental group of B with respect to B naught. This mapping is the monomorphism. We already know that whenever we have a continuous mapping, say from E to B, then there is a homomorphism induced by this continuous map, and that is given by this P star, which is from fundamental group of E to fundamental group of B. So now in this theorem, we will prove that if P is a covering map, then it is a monomorphism actually. Secondly, we will prove that if H is image of this mapping P star, then our lifting correspondence phi lifting correspondence mapping phi induces an injective map. Say this is capital phi from pi 1 B naught over H to P inverse B naught. So this is basically this phi mapping lifting correspondence map phi is from pi 1 B naught to P inverse B naught. Now this is from the quotient group of pi 1 B naught to P inverse B naught. So this is injective map, and this is induced by the lifting correspondence phi. And this is a mapping of the collection of right cosets of H into P inverse B naught. And this mapping, this mapping is bijective if E is path connected. So if E is path connected space, then phi is bijective. And the third part is that if we take F to be the loop in space B based at point B naught, then its path homotopy class will belong to the group H if and only if F lifts to a loop in E based at E naught. So this part basically proves that if F is a loop in space B, which is based at B naught, then its lifting will be also a loop in E based at E naught, if and only if that path homotopy class of that path F belongs to H, means it belongs to image of the homomorphism P star. So now we will prove it. Firstly, we prove the first part In the first part, we have to prove that the homomorphism P star is basically a monomorphism. That means we have to prove only one part. So we have to prove P star is 1, 1. We will prove that the kernel of P star is just an identity element. So we will take a loop H curl. So let H curl this be a loop in space E based at point E0. That means we are basically assuming that this homotopy class, this is an element of this fundamental group of E based with respect to point E0. So we assume that this is a loop, or we assume that this homotopy class H curl, this is a homotopy class whose image is the identity element under P star. So let this be a loop such that P star of this element is identity element. That means we are basically assuming that this path homotopy class of H curl, this belongs to kernel of P star. So we will prove that this element is actually identity element itself, so that the kernel contains only identity element, so that the mapping will be monomorphism. Now, if this is identity element, then by definition of P star, basically we are saying P circle H curl, this path homotopy class, this is identity element. And we know the homotopy class is identity element if and only if this path P circle H curl, this is homotopic to constant loop. Yeah, constant path. Constant loop in space B. Now, if this is homotopic to constant loop, so we can assume that capital F is the homotopy between this P circle H curl and the constant loop. Now, if F is the homotopy between P circle H curl and a constant loop based at point B naught in space B, then its lifting F curl, the lifting F curl of F, that is basically a path homotopy, because we have already proved that if F is a continuous mapping which maps 0, 0 to point B naught, then its lifting F curl, that will be a unique mapping, a unique lifting which maps 0, 0 to point E naught. And if this F is a path homotopy, then F curl is also a path homotopy. So if F is a path homotopy between P circle H curl and the constant loop based at point B naught, then its lifting, the unique lifting F curl of F, that will be a path homotopy between lifting of P circle H curl, and lifting of P circle H curl is basically H curl, and lifting of constant loop based at B naught, and that will be lifting that will be constant loop based at point E naught. So basically F curl is a path homotopy between H curl and constant loop based at E naught. So we have proved that H curl and constant loop, they are homotopic to each other, path homotopic to each other. It means path homotopy class of H curl, that is identity element. So we have proved that if image of H curl under P star is identity element, then H curl is itself identity element. It means P star is 1, 1 mapping. So being homomorphism, it is basically a monomorphism. Now we come to second part. In the second part, we have H, which is image of P star. So H is P star of pi 1 E naught. Now we want to prove the lifting correspondence phi induces an injective map capital phi. So first of all, this capital phi is induced by small phi, and that is obviously true by group theory, by basics of group theory. Because in group theory, if we have a mapping, say phi from a group G to, let us say, group A, and we have another mapping P, which is monomorphism. Let us say P star, which is monomorphism from group, let us say G dash to G, such that H is image of P star. Then this phi induces a homomorphism, capital Phi, from G by H to A, which is defined by this phi of Hg given by phi of G. So phi of capital Phi of Hg means phi of right coset of corresponding to the element G belongs to G, that is equal to phi G. So if we have a given homomorphism phi from G to A and P star a given homomorphism from G dash to G, which is a monomorphism, and H is image of P star, then this mapping phi, this which is G to A, this induces a mapping from G by H to A, and this mapping will be defined by phi of Hg is equal to phi G. Now in this result, we have to prove that this phi, lifting correspondence phi, induces a mapping capital Phi, which is injective here. So we want to prove that this mapping is 1, 1, capital Phi. So we will prove, basically to prove 1, 1 here, we will prove that phi of f is equal to phi of g if and only if f belongs to hg. Because in this case, if we want to prove this capital Phi is 1, 1, that means we want to prove basically this thing, that phi of hg is equal to phi of hg1 is equal to phi of hg2, or we can say phi of hf. So we have to prove phi of hf is equal to phi of hg if and only if hf is equal to hg. To prove capital Phi is 1, 1, we want to prove that phi of hf is equal to phi of hg if and only if hf is equal to hg. That means we want to prove that phi of small phi of f is equal to small phi of g if and only if f belongs to hg. So to prove capital Phi is 1, 1, we need to prove only this thing, that small phi of f is equal to small phi of g if and only if f belongs to hg. So in this particular part, we will prove that if f and g, these are loops in space B based at point B naught, or we can say if these two path homotopy classes belong to pi 1 B naught, then we want to prove that phi of f is equal to phi of g if and only if f belongs to h star g. So we want to prove this thing. To prove the capital Phi mapping is 1, 1. So now we are assuming that f and g, they are loops in space B based at point B naught. So let us assume that f curl and g curl, these are the liftings of f and g. These are liftings, unique liftings basically, of f and g in space E starting at point E naught. Then by definition, phi of f, this is end point of f curl, and similarly phi of g, this is end point of g curl. So it is g curl 1. So we want to prove that phi of f is equal to phi of g if and only if the path homotopy class of f belongs to h star path homotopy class of g. So firstly we assume that Firstly, we assume that path homotopy class of F belongs to H star path homotopy class of G. And then we will prove that phi of path homotopy class of F is equal to phi of path homotopy class of G. Now, if F belongs to H star G, then basically F is equal to H star G for some homotopy class H belongs to H. And we know that H is basically P star of pi 1 E naught. It means if this H belongs to this image of P star pi 1 E naught, that means H is basically equal to P circle H curl for some H curl belonging to pi 1 E naught. By definition of P star of H curl is equal to P star of homotopy class of H curl is equal to homotopy class of P circle H curl. So for some homotopy class H curl belonging to pi 1 E naught, it is P circle H curl. It means we can say that H is equal to P circle H curl for some loop H curl in space E based at point E naught. Now we know that H curl is a loop based at point E naught. So end point of H curl is E naught. And we know that the starting point of G curl, that is E naught, because we have assumed that F curl and G curl are liftings of F and G beginning at point E naught. So it means H curl star G curl, this is well defined product of paths. And this is basically lifting of H star G, because H is equal to P circle H curl, which means H curl is lifting of H and G curl is lifting of G. So this H curl star G curl, this is lifting of H star G. Now because F is H star G, from this F of this is H star G, it means the liftings, if these two path homotopy classes are same, it means the two paths F and H star G both are path homotopic to each other. So their liftings, they also are path homotopic to each other and they end at same point. So their liftings, F curl is a lifting of F beginning at point E naught, and H curl star G curl, this is a lifting of H star G which is beginning at point E naught. So these two liftings, they are homotopic and they end at same end point, end at same point, and they are homotopy to each other. So if they end at same point, that means F curl at 1 and G curl at 1, they are same, because end point of this is F curl 1 and end point of this is G, same as G curl 1. So F curl 1 is basically phi of homotopy class of F and G curl is phi of homotopy class of G curl. So we want to prove this phi of F is equal to phi of G. Now conversely, we will prove that if phi of F is equal to phi of G, then the homotopy class of F belongs to H star homotopy class of G. So now let us assume phi of F is equal to phi of G. Now if these two are same, then by definition of phi, F curl 1, G curl 1, they are same. That means F curl and G curl, they end at same point of the space E. It means F curl star reverse of G curl. F curl star reverse of G curl, this product is well defined because the end point of F curl and end point of G curl are same. It means end point of F curl and starting point of reverse of G curl are same. So this product is well defined. And since they have same starting points, F curl and G curl have same starting point at point E naught. So this product of paths, basically this is a loop at point E naught, and it is a loop based at point E naught. Let us suppose that this path is basically H curl. Assume that this is H curl. Now, if H curl is equal to this, then H curl star G curl. This is equal to F curl star G curl bar star G curl. Now, G curl bar star G curl, this product is homotopic to the constant path based at point based at any point, then F curl star the constant path. This will be homotopic to F curl. So this path is basically homotopic to F curl. So H curl star G curl is homotopic to F curl, which means their path homotopy classes are same. So these two path homotopy classes are same. Now, if these two are path homotopic to each other, H curl star G curl and F curl, if these two are path homotopic to each other, and let us assume that F curl, that is a path homotopy between these two mappings. Let F is a capital F curl is a path homotopy between H curl star G curl and F curl, these two paths. Then the composition P circle F curl, this is a path homotopy between the paths P circle H curl star G curl and P circle F curl. So if F curl is a path homotopy between these two paths, then the composition P circle F curl, this is a path homotopy between P circle, this path H curl star G curl and P circle F curl. And what is P circle H curl star G star? This is H star G, because we know H curl star G curl, this is lifting of H star G. So P composition with this mapping is just H star G, and P circle F curl, this is just F. So this is path homotopy. P circle F curl is a path homotopy between H star G and F, where we can assume that H is P circle H curl. So now we are saying that H star G is path homotopic to F. It means F is equal to H star G. Their homotopy classes are same. So we can write it as homotopy class of H into homotopy class of G. And this belongs to H star G. Because this is small h, this belongs to the group H. Because of this reason that H is P circle H star, it means the homotopy class of H. This is homotopy class of P circle H curl, and this is equal to P star of H curl for some H curl. So this homotopy class of H belongs to image of P star. That means it belongs to capital H. So we have proved that if phi of F is equal to phi of G, then the homotopy class of F belongs to H star homotopy class of G. So it proves that the lifting correspondence induces a mapping capital phi, which is injective. And further, we want to prove that if E is path connected, then this capital phi is surjective mapping. And that is obviously true, because we know that if E is path connected, then small phi is surjective. And if small phi is surjective, then capital phi is also surjective. Now we come to third part. Now in the third part, we want to prove that the lifting of a loop is again a loop if that loop f that if the homotopy class of that loop f that belongs to H. So in this theorem, in this third part, we can say we have proved that phi of f is equal to phi of g if and only if f belongs to H star g. So we apply this case when g is a constant loop. So when g is a constant loop, then phi of g, which is basically g curl at 1. Now since f and g, they are paths starting at point e naught, and if we take g to be the constant loop, so endpoint of g, that is also e naught. So phi of f is equal to e naught if and only if this f belongs to H star, the homotopy class of constant loop. Homotopy class of constant loop is just the identity element of the fundamental group. So it is H star identity element, which is basically H. So we are saying phi of f is E naught if and only if the homotopy class of f belongs to H. And phi of f is equal to E naught. It means f curl 1, this is E naught if and only if f belongs to H. So this proves that the lifting f curl of the path f, that is also a loop based at point E naught if and only if the homotopy class of f belongs to H. And this we want to prove in this third part. And this completes the proof of the theorem.